Well, welcome back to videos. It's been a little while since we've had a new one, and hopefully with some of the feedback that you guys gave me on the earlier videos, we can make these going forward better and better, and try to make them a little more effective for everybody. We'll give it a try. As you see there on the opening slide, today's topic is with matter, its properties and its changes, as well as how we classify matter. So that's how we'll start things off, and I think you'll find that this unit has a lot of contrasting terms, so I'll kind of point those out to you as we go along, and it can, I think, go a long way in helping it make it easier to get the ideas straight, keep the ideas straight, and not confuse things as you go. By the end of this video, hopefully you can tell the difference between chemical and physical changes, chemical and physical properties, intensive and extensive properties, as well as the differences between mixtures and substances, compounds and elements, the terms heterogeneous and homogeneous, and what a phase is versus an interface. Now, I wouldn't write all these down here as a list because those will all be coming later on in the video, a bit at a time, and explaining each of those pairs to you as we go. But as I say, as you go through this unit, you're going to find a lot of these paired terms that are not necessarily opposites, but they kind of go together and complement each other, and we use them to kind of separate things into these two classes or these two categories a lot of times. So as we go, keep those things in mind. So classifying matter is the newer stuff, and some of you had the notes on those changes, so this is where the new stuff picks up for you. Classifying matter is an important thing that we'll do for all materials throughout this unit and then into the rest of the year. You want to be able to classify any material that you see as one of basically two main categories, and then within each of those, two smaller categories. So we sort of subdivide it down. And you'll see what I mean as we go. So again, think about matter as being anything that has mass and volume, solid, liquid, or gas. Matter comes in what we call phases. Phases are regions of matter that have their own properties. So a single phase is a part within a larger whole that has its own set of properties. And I'll show you some examples of phases within some pictures here in a couple of moments so that you see what a phase is. It's quite simple. It's a region within a larger material often. And so it has its own properties of color, of texture, of state. In some way you can tell it from its surroundings. And if there's only one phase in a material, then it's the whole thing. But it's how we sort of look at a region within a whole. And I'll show you some examples, both chemistry and then sort of real life here in just a moment. Phases then can be in contact with each other, and where they touch or are in contact with each other is called an interface. You can think about it like, take that word apart, interface. Sounds a lot and looks a lot like interphase, and interphase sort of between the phases, or crossing between the phases where the two phases touch. And so this is where physical and chemical changes can happen. It doesn't have to be happening. Not every interface has a physical or chemical change happening, but every physical or chemical change we can pretty much always trace those back to some interface if we look close and think about it hard enough. So interfaces are where two phases touch or are in contact with each other, and where a change can occur. So in this picture you see what we call a precipitate, and it looks like a kind of yellow blob of something or other in a clear liquid in a test tube. That yellow stuff is called a precipitate, and what you're actually seeing there are micro-sized crystals of some yellow compound, and they're sort of sinking through or swirling through the test tube. You'll be making precipitates like this in lab, in a number of different labs, including perhaps number 6. And so you'll see this throughout the year, and you may even see this exact precipitate if we do a certain lab in your lab manual. But what I want to point out to you on this picture are two phases specifically. So here you see at the top here, that's not the liquid phase. I got to fix that. The arrow should be pointing to the clear liquid around the yellow stuff. So within the picture, fix that arrow. There is a clear solution area here. And there's also a clear solution down at the bottom of the test tube. That's sort of, when we think about it like water, it's probably not water, at least not plain water, but it's the clear watery looking part of what's in this test tube. Above it, that's pointing to another phase, which would be air, I suppose, but that would be a clear gas phase, so that's my mistake. The other phase in the test tube is the yellow stuff, or because it's a solid, those are little crystals, we would say that's a yellow solid phase. Now when you do this in lab, it looks almost liquid. It looks like a thick liquid floating through the tube, but it's actually many, countless tiny crystals. And so when it gets down to it, we're looking at a solid phase where we can't see a solid chunk, but those little crystals then will actually settle to the bottom of the test tube sort of precipitate to the bottom, like precipitation. So that's why they get their name. So in this test tube there are two phases, the yellow phase and the clear liquid phase. And again, the arrow is not quite pointing to that, but that's the idea. An interface then is where those two phases would meet. And so you see here that all around the yellow stuff, where it's touching the clear liquid, would be considered the interface between the yellow and the clear. That's one example in lab. So we could say this test tube contains two phases and one interface. Now this is a little more real life example, looking at an upside down s'more blizzard from Dairy Queen. And in this particular picture, everyday life sort of stuff, we can find phases too. So for example, there's an ice cream phase here. We would describe it as having properties like being white, and if it's a solid or a liquid is a little bit hazy as far as ice cream and blizzards go, but that's not so important, as we can tell it apart from what else is in the cup. Right? So we've also got this tan graham cracker phase, so that's distinguishable because it has a different color. We'd probably say that that's a solid for sure. And then there's this candy phase, which looks like it's got two phases of its own. So there's chocolate wrapped around a center marshmallow phase, and those little marshmallow squares or whatever they are that Dairy Queen puts in there. And so we've got in this picture just of what's in the cup to eat. There's more or less 3 or even 4 different phases: the ice cream, the graham crackers, the chocolate, and the marshmallow, which for a s'more blizzard makes perfect sense. Now there's lots of interfaces in there. Wherever chocolate touches ice cream, there's an interface. Wherever ice cream touches graham cracker, there's an interface. Wherever chocolate touches marshmallow, there's an interface. So there's all kinds of them in here. Nothing all that important happening necessarily where those phases are touching, but those would all be classified as interfaces within this mixture. And the last one then to show you then is this example of a Coke in a glass with ice cubes in it. And I bring this one on because I want to show you that when we talk about changes happening, they're happening at an interface. And so for example here we see two physical changes quite obviously happening. One, the ice cubes are melting, and that happens where the ice cube phase, the solid ice phase, touches the liquid Coke phase. Melting happens on the surface of the ice cube. And the other one is condensation, which may or may not show up very well for you depending on the screen that you're watching this on. But there's condensation happening on the outside of this glass, and that happens only where the glass, the cold glass, touches the air, and that's an interface too. It's not one we think about as much in this picture because we're focusing on the drink, but there is an air phase surrounding the glass, and there's a glass phase, and so where those touch, condensation happens. Moisture or water vapor and cold glass come together, and there's condensation. So we have two physical changes happening in this picture, both of them at interfaces. And one more example here is a picture of 2 ALKA-Seltzer tablets sinking their way into a glass of water, something that we see in lots of ALKA-Seltzer commercials and that sort of thing. And those are chemical changes happening, and it's happening again at an interface. So ALKA-Seltzer splashes into water, starts to bubble like this, and there's a chemical change happening where the ingredients in ALKA-Seltzer are combining when they get into a solution form, and one of the products that they make is a new gas. In this case it's carbon dioxide bubbles being made, but if you can look really closely here, the bubbles form right exactly where the ingredients of the tablet touch the water. And so there's an interface right there. The tablet's contents are dissolving and they're immediately reacting with each other, and we get this chemical change forming a new gas, as well as some other things that are in the liquid after you as you're drinking it, but we're not too worried about those at this point. So a couple of examples of how interfaces are the place where changes happen, and they only happen there. You won't see this tablet dissolving from the inside out. It only happens from the outside in. And if you don't drink ALKA-Seltzer often, you can maybe see this in like an airborne tablet during cold season. It does the same sort of thing, same chemistry. So how do we classify matter? What I want you to do is in a sheet of your notebook paper, preferably a fairly large sheet, maybe even start for this diagram with a fresh page of paper, and draw this little sort of chart with me as we go. So you'll notice this becomes sort of a flow chart for matter. We're starting at the top in the black rectangle and working our way down to the red and green, and then splitting those into 2 separate boxes of their own. So if you put this into a notebook paper page, it sometimes works better if you turn the page the wide way. But if you like writing on the lines, you can probably do it the regular way as well. We want to start at the top of a fairly big section of paper, and if you've got about maybe 3/4 of a page here on the sheet you're working on, that should work too. Depends on how big you write. So we'll start in that top box, then kind of work our way down and split it, and then split it into 2 more at the bottom on each side. So kind of classifying matter as a flow chart. In the first box, you want to put the term material. A material is a very vague, very general term in science and chemistry. A material is really any kind of matter, specific kind of matter that we can give a name to. So you can see the name of the word pizza that conjures an image in our head. Pizza is a material. Carbon dioxide gas in the air that you breathe is a material. Skin is a material. Chocolate is a material. Just about anything we can think of that's matter can be named, and so it is a material. And so it's a very vague term. All materials then can be split into two categories. And on the left you see the term is substances. A substance is a material that has a definite composition. And by definite composition we mean it's always the same everywhere you go, all the time on Earth. And so if I have carbon dioxide, it's CO2, carbon and two oxygens, all the time everywhere. And it doesn't matter if I'm here in Bismarck, North Dakota, or if I'm in Moscow, or if I'm in Australia, or if I'm in Africa. It doesn't matter where I might be. It's always going to be carbon dioxide, CO2. It's got a very definite composition. Same thing with all the elements on the periodic table and any compounds that we can think of. Sugar has a very specific composition. Salt has a composition that matters the same everywhere. Water's H2O no matter where you go. So those are all substances. They have a definite composition that doesn't ever change. On the other side, though, is mixtures. Now, mixtures have a variable composition. It's just the opposite. A variable composition means it might have a name, like pizza, but it's different everywhere you go. And if you go to a Domino's pizza and compare that to a Papa John's pizza, or a Pizza Hut pizza, or Papa Murphy's pizza that you bake at home, or DiGiorno's or anything, it might be a pepperoni pizza, but everybody's is different, but it would still have the same name. So pepperoni pizza is a mixture because it can vary from place to place. Even tap water can vary from place to place. If you've ever drank, say, well water from a rural source, maybe on a farm or something, you know it may have a little funny taste to you. And it's because it has different trace minerals in it that hopefully aren't harmful to you, but they make it funny taste in your mouth because you're not used to it. But that's tap water in that farmstead or something, as opposed to tap water in Bismarck. And even day to day, month to month, there can be variations just in Bismarck tap water. So those are all mixtures. The air we breathe is a mixture too, because it has all kinds of different things in it, and from day to day those things change. The humidity can change, the amount of pollution in the air can change, lots of stuff. So air is a mixture, but we would call it air every day. No matter how much of it we breathe, no matter where we're breathing it, we really call it air, but it's different everywhere. So that makes it a mixture. And there's lots and lots of others as well. On the substance side on the bottom, we've got elements. Elements are, of course, what we've been studying all along with electron configurations and things. They're one kind of atom only. They have the same number of protons. They have an atomic number that makes them an element. And so there are about 92 or so naturally occurring elements plus the synthetic elements that are on the periodic table. So there, you could, if you took it upon yourself, you could memorize all of the elements. It's a very small list compared to the compounds and other things. I'm not going to ask you to do that, but you could. And you see here the one word at the bottom that we haven't touched on yet, so that's homogeneous. We'll begin to that word. It just means that elements have one phase only. So you won't see layers or zones or regions within an element. It looks like copper all the way through, for example. So elements are one kind of substance. They're the same everywhere. Copper is the same everywhere. Oxygen is the same everywhere on Earth, so it's a substance, and it has only one kind of atom in it. The contrast to that is a compound, which is still a substance because, like carbon dioxide or water or sodium chloride, they're the same everywhere on Earth. They're the same formula, they have the same atoms in the same constant ratio all the time. And of course there are millions of compounds, but each of them is very consistently the same. And like elements, they're also homogeneous or homogeneous because they have one phase. You won't look at a bowl of salt and see like some salt that's saltier than the rest, or some salt that's a different color. If you do, there's something else in there. Salt's the same color throughout. If you've got to, pour it into your measuring cup or something from your kitchen cabinet, or if you pour sodium chloride out in a lab in class, it looks the same throughout. So that makes it homogeneous, one phase. We can also split the mixtures into two categories, and again you see the term homogeneous here. Homogeneous mixtures are those that have one phase throughout. They can vary from place to place, from day to day, so they're mixtures, but they're homogeneous because they have one phase throughout. Air, as I mentioned before, is a mixture, and air, we would say, unless you're in a very polluted place like Mexico City or Los Angeles or some other big metropolitan area, you probably don't see the air that you breathe. And so when we're looking at air here at home, you're breathing air, you can't see layers in it. It looks the same throughout. and yet it has lots of different substances combined into one breath: nitrogen, oxygen, carbon dioxide, water, argon, and any other pollution that might be in the air that you're breathing. Lots of stuff in there, but you can't see the layers. It's all the same throughout. So it's homogeneous as a mixture with several substances mixed all together. And then the partner to that is a heterogeneous mixture. Heterogeneous mixtures are those that have two or more visible phases in them. And so they're not uniform throughout necessarily. There can be layers, there can be parts that are different than others, and heterogeneous mixtures look very obvious. They're kind of the one that's different than the others because elements, compounds, and homogeneous mixtures are all homogeneous. Heterogeneous mixtures are just the opposite, heterogeneous, and they have more than one phase in them. So I'll go back to that pepperoni pizza analogy. Talk about pepperoni pizza, you can see the pepperoni, you can see the cheese, you can see the sauce, you can see the crust. Those are at least 4 different phases within each slice of pepperoni pizza. You can see those very separate very easily. They have their own properties, and so that would be considered a heterogeneous mixture. In class, in lab, you just saw here a moment ago on the screen the yellow precipitate in the test tube. That would be a heterogeneous mixture because there are 2 very obvious different phases involved. So that's a couple examples for you. So there's your finished chart. Hopefully you've got it. What we'll be able to do then is take any material that I give you and put it into one of those 2 boxes, substances or mixtures, and also into one of those 4 boxes at the bottom. Classify it and split it out from there. So just to kind of formalize heterogeneous versus homogeneous, let's put that on the screen here for you and have you put it down too. The term heterogeneous just means it has 2 or more phases. And some mixtures are heterogeneous, obviously, and also have interfaces, as opposed to homogeneous, where we have only one phase. And all substances, both compounds and elements, as well as mixtures, are homogeneous. Some mixtures, rather, are homogeneous. In these, there are no interfaces, because as long as you have only one phase, it can't be in contact with anything else. You have to have at least 2 phases to have an interface. And so none of those would have that. Again, if we go back to the pictures from before, this is a heterogeneous mixture. You can see 2 phases in it. This is a heterogeneous mixture because there are lots of phases involved, at least those several that we wrote before. And this would be, Coca-Cola would be a homogeneous mixture, the liquid itself, although you can argue that the bubbles make up their own phase, so I could see that going both ways. And once you put ice into it, you've made it heterogeneous because the ice and the pop each have their own visible phases. So without the ice, Coke, you could argue, is homogeneous. With the ice, it's definitely heterogeneous because there's 2 different parts to this mixture: the Coke phase and the ice phase. And again, if you argue the bubble phase is its own, then you've got a 3rd phase there.